Welcome back to the lab. Today we're going to talk about the principles of object-oriented programming and how you can use them to make your code easier to read, easier to maintain, and really easier to write too. Before we get into all that, check out this short message about our latest design sponsorship. Maybe you want to control something connected to mains, but don't know how to do it safely. We can help with that. That's what this contest is all about. Okay, that sounds great. Here's how to enter. Tell us about yourself, tell us about your project, tell us how we can help. Best of luck. I hope you're as excited to work with me as I am to you. So thank you for watching EEforEveryone, and I cannot wait to hear about your next great project. Welcome back. Let's dive into our code. I've taken a couple formal classes on writing software. Not a whole lot, but at least a few. And after taking these classes, there were a couple subtle things that I changed in my code after learning what those professors had to say. Ultimately, there is no replacement for experience, but if you keep these tips and tricks in mind while you're writing code for your next project, you could see a massive improvement in the quality of your code and how easy it is for you to keep your mind wrapped around what you're trying to do by breaking down problems into smaller pieces. First of all, before I start telling you what object-oriented programming is and all these details, let's start from the fundamental question. Why would you ever want to improve the quality of the code that you write? Well, on a basic level, the better your code is organized, the easier it will be to write software that works the first time. If your code is good, you'll spend less time debugging the tedious issues like typos, and your effort will be focused on the big issues like the math or the algorithms that are driving the design that you're trying to test. The better the code is, the easier it will be for you to come back later and add features into what you've already been working on. Sounds great, right? How do I get in on that? Well, to help guide us down this path, I would like to talk about 3 different types of code that I've watched myself write. Now, this is an oversimplification, but from what I've seen, there's fundamentally these 3 different types of code. There's spaghetti code, which is where almost everyone starts, and it probably has a formal name, but if it does, I can't remember it, and it's not worth remembering because it's terrible. This is code that's probably written all in one file, meant to be executed from top to bottom, is probably thousands of lines long, and hopefully has some comments somewhere. Adding new functionality can be a minefield since all variables are declared in this one file, and that means that you could be stepping on the toes of your other functions by reusing the wrong variable or trying to declare a variable with the same name. It just becomes a mess. This is where object-oriented code, which at its core means that software is developed where functions are logically grouped with the variables that are needed to perform those functions. Rather than putting everything in one giant file, there's one set of variables and one set of functions, and they're stored in each file. And this just helps to keep you organized. It keeps it really clean. There's functions to create, destroy, or use these groupings of variables and functions, and these groupings are referred to as objects. Functions in object-oriented code are generally called methods. So there's some code that lives in between these 2 options, and this is code that gets written while learning how to write good object-oriented code. Software definitely has an element of style to it, and it's important to develop your style. While everyone has their own style, get your code reviewed, get some feedback on the code you're writing, and keep tweaking your style to make your code better so other people can read it. Every time I start a new project, I find that my approach to architecting everything gets a little more refined each and every time. We'll talk a little more about that later. But here are a few principles that I repeat in my head over and over and over again when I'm writing software. I've heard this eventually becomes intuitive and you don't need to think about it so hard anymore, but when you're first starting out, and I still need to do this, internalize this, repeat it over and over and over again. First, don't write a function longer than what you can see all at once on your screen. If you need to read more than what you can see on your screen, you'll be scrolling up and down, and it probably means that you're putting too much in one function. If you need to use an equation or algorithm twice in your code, define a function to do it. Don't ever copy paste. What this does is by copy and pasting, it introduces you to have the same function, but it has slightly different performance because you fixed an error in one location and it didn't get copied over to the second location. It also helps you with the first point since you're reducing the amount of lines of code it takes to do each thing. If in your code you're in a situation where writing an unknown value to your function could break things, that's where you need to use something called a setter. And what that does is it's putting some logic between present you and future you. And this setter is a function that you define to make sure that the value coming into your code makes sense for how it's going to be used in your context. Fourth, comment. Always comment. Half of your code should be comments. You cannot have, well, you can probably have too many, but I've never written too many comments in my code. In our UPS project, what we wanted to do was use objects to make our main loop as clean as possible. We offloaded as many functions, as much code as we can to the objects that live underneath it. How can we do that? For example, if we had a class called myClass, it would have something called myClass.refresh, and that might be a method that we call in the main loop to refresh the user interface. All right? MyClass.voltage might be a variable stored within that class that would represent a voltage. This isn't really all that different from having a function called refresh in the main loop of the program and a variable called voltage for that function to use. The important distinction here in the object-oriented case when compared with the general case is that we're talking not just about any voltage, we're talking about exactly the voltage that's used and expected by my class. Now that's a really basic example. Let's apply this to our UPS. Ultimately, there's still a main loop in every program, but in this case, we don't have any low-level decisions or actions here. Everything contained in the main loop is a logical action. One level deeper, the top-level code is aware of the objects that it can either send information to or get information from. For the UPS, those are the ADC controller, user interface, and control loop classes. The ADC controller provides the system with measured analog information after that's filtered, averaged, and scaled from ADC counts into logical units like amps or volts. The user interface takes in a data structure containing everything known in the system, every fan state, every voltage measured, every current, any and all information is passed into the user interface, and then the refresh command is given periodically. Any UI action requiring information from the other objects in the main code, well, see, that's where these things get linked together. That's what the main loop is for, to link together the logical level stuff that's defined in the lower level functions. The main loop is where we funnel information from one class to another when they don't really have any knowledge of what's going on in any class. They just know that one has voltage and the other one needs it. But we can't quite stop here. This structure for our UPS has a couple more layers. The ADC controller and UI both have another set of objects that they're aware of that live underneath them. The main loop doesn't know about them, but they do. These classes help to break down the high-level command of turn on a fan when it gets too hot and display the inverter output voltage closer to hardware-level actions, toggling pins, sending bytes on a communication bus. We're getting one level closer to the hardware. On the ADC controller side, the temperature sensor translates measured voltage into a temperature, and then the fan controller translates the current temperature into a fault code and a fan state, on or off. The UI is aware of a lower level object called a quad screen, and what this quad screen allows for is displaying 4 variables on one page of our display. This object is aware of an even lower level object, which takes in 1 page worth of data and then translates that into I2C commands that are sent out to our display. Pretty wild, huh? One reason why this is so great is in case something changes. Like, if our display needs to change because we want a different one, if our 16:2 LCD gets too small, all we have to do is swap out our display driver to communicate over SPI or maybe still I2C, or move that function into another microcontroller altogether and hook it up over the same communication interface. What'll need to happen is the process of boiling that system data into pages on a screen will still be the same. So the hardware change won't really rip up anything on the top level code. Only 1/3 of this UI really needs to change, and that's the hardware link from pages of a screen to bytes on a communication bus. The other time that this structure becomes incredibly helpful is when multiple processors get involved. This diagram right now is a logical structure of our software, but it's hiding some critical details about how we actually implemented it. Our software, in reality, is actually split across 2 physical processing cores. When the UI wants to show a piece of information that it doesn't know, but the inverter microcontroller does, the microcontroller link object is used to reach out into that partner processor and request the data. That's not always a viable solution. You can't always do this, since some data is time critical. You can't use something like this to transfer time critical data unless the criticality is seconds and not milliseconds. The added delay and risk of corrupting data when forwarding information to a partner micro might not always be acceptable. For example, if our PSOC5, if the high-level micro was measuring analog voltages used for making decisions about the control loop, this would never work. We simply cannot send information quickly enough across the UART link we've architected to make that happen. To lean into this tangent about our UART communication link for a moment, could we have used SPI, I2C, CAN, or any other communication protocol? Yes. Yes, we could have. Why didn't we? Well, these processors are pretty much operating independently. They really only need to sync up once every couple hundred milliseconds just to pass information about current state and make sure that the ADCs are still functioning correctly. These microcontrollers don't need to rely on each other for anything that's really critical in the order of milliseconds. Everything's on the order of seconds. So the communication link really doesn't need a lot of throughput. These processors live literally inches away from one another on the PCB, so we don't really need the robustness or data rates that come along with more advanced protocols or differential signaling. And quite frankly, I was running out of pins on these micros, and we don't need the added cost of the more complex protocols. UART can sometimes be viewed as a little basic or a little hacky, but I just don't believe that there is a technical reason that demanded more robustness than what a simple UART can offer. After all, we built our own protocol on top of the UART that allows for sending 32-bit words of data with multiple data types. If we want to include a checksum or redundancy in that protocol to increase the robustness of our communication, we certainly can. Let's come back to Earth for a moment. The diagram that you see now shows arrows connecting everything that has direct knowledge of everything else. The ADC controller is aware of the hardware ADC peripheral. The UI is aware of the quad screens. The main program is aware of the UI. The way that we've drawn out this architecture looks a little busy. Let's redraw this diagram in a way that shows the relationships a little better. Our redrawn diagram shows much more clearly how we wrapped objects inside of objects to keep the code simpler on the high level, on the top level, rather than trying to write one gigantic set of functions and variables that are used to display every piece of information known to the user in the UI object. We took on smaller bite-sized chunks of functionality, and what we did is we wrapped them into larger logical groups. Did that make sense? Most of these classes and structures were pretty easy to architect and link together, and I'm really happy with how the UI class came out. Let's talk about that one a little bit. I believe that creating a text-based UI in a way that doesn't turn into thousands of lines of messy code is one of the most difficult types of software to architect in a sustainable way. However, what we did for our UPS was create an array of screen objects, a main menu screen index, and then define a screen transition for every one of those indices. If we need or want to add more screens that allow for displaying more information, all we have to do is add a couple more screen objects to our array. With the objects added, then we just need to link our screens to the system data they should be displaying. I think this UI code came out super clean, and it only took a couple hours to architect. I'm blown away with how much better this whole software architecture is than the things that I've architected in the past. I've always tried to write my code in an object-oriented way when I'm writing on an embedded micro, and while I'm sure that there's some software developers and engineers out there that are thinking of 1,000 ways this code could be better, I think it came out pretty darn good for a hardware engineer writing code. I mean, we are infamous for creating completely unsustainable train wrecks. And as much as I hate to admit it, I think that I actually owe my organization to an unforeseen challenge. You see, object-oriented code is supported really well by languages like Python, Java, C++, C#, but the PSOC 4 and 5 processors don't support any of those languages, not even C++. And apparently there's a way to fight with the Eclipse integration in PSOC Studio to hack it together and get C++ to compile, and I did that, but once I got C++ to work, I couldn't generate new hardware abstraction code for the microcontroller because PSOC Creator didn't want to compile the C++. Even more, I had problems getting the generated C code from Cypress to compile in the Eclipse IDE. After a couple hours of this madness, it was just getting tedious and bad, so I just said, all right, whatever, I'll stick with C. I will develop my C code in PSOC Creator. Fine. There's only one problem. C doesn't support objects. It doesn't support classes at all. So how in the world did we use this C compiler to architect our code in an object-oriented way? Well, no compiler can stop me from, no, I'm just kidding, but really, no compiler can stop me from forcing myself consciously to write code in an object-oriented way, even if the language or compiler doesn't have predefined structures or methods of helping me to do it. This conscious effort making me to get into a flow of making some messy code, that really kept me honest to the 4 principles that we laid out at the start. Now, would I recommend taking on the challenge of writing object-oriented code in C if this is your first time writing object-oriented code? No, absolutely not. Get your foundation in an object-oriented code using a language that supports it. The C compiler throws entirely unhelpful and mostly misleading error messages when making simple errors, referencing or dereferencing nested variable structures that are used throughout our design. The structures that you'll need to use when writing object-oriented code. This, along with memory allocation and deallocation, all happens a lot nicer when using C++. In fact, some of that happens automatically. Using C means manually managing memory in your software, introducing the potential for memory leaks or using variables without initializing them properly. Not a concern when C++ proper is used. Constructors, destructors, and initialization routines can be called automatically when writing object-oriented code in C++. To give you an idea of what object-oriented code looks like in C, here's a couple snapshots. What you're seeing is pointers. Pointers, lots and lots of pointers, and variable structures, or enums. To help us make this code object-oriented, I started every function or pound defined with a prefix and 2 underscores. The system ensures that all functions have a unique name throughout our project. In this case, since we don't have a proper C++ compiler compiling object-oriented code, it's still possible to make variable name and function name pound-defined conflicts that wouldn't normally be possible. So when I was writing code for a function in the display class, I'd start it with the prefix twi_display followed by 2 more underscores. The effect? This prefix is kind of like the same thing that we had with the dot notation. And that name was consciously made to be the name of the file itself. There was nothing making me do this. There wouldn't be any compiler error. I could have called it whatever I wanted to call it. But what this does is it makes it really easy for me to remember which file that function is defined in, because I have a file called twi_display and a function with a prefix twi_display. Yeah, like that? Self-documenting code. This prefix also meant that as long as we didn't create 2 files with the same name, we would never have a variable name conflict or a function name conflict because we're calling every function with the file name as a prefix. So, conclusion time then. I had, as much as I hate to admit it, a little bit of fun writing this code. We're well on our way through the software, but there's still a lot to do. We have enough code written to test out many elements of our design, so I think this will keep us busy with the hardware for a while. But if you like what you saw today, subscribe to be notified of our future videos where we'll power on our first prototype with a control loop running to test it under load. If something pops up out of the woodwork, some issue we need to debug, I guess that means our testing won't be done until we find the root cause of those issues and mitigate them with design tweaks. I think that staying organized is great, and if you learned something about organizing your code today, let me know by hitting the like button on this video, chatting with us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for Everyone, and thank you for staying till the end. Bye!